für zwei weitere Vorträge. Den nächsten Vortrag, den ich ankündigen darf, ist von Peter Borger. Wir werden wieder in eine Welt vordringen, die man nicht mit einer Lupe, wie uns Harald Binder empfohlen hat, immer dabei zu haben.
The next
kann man nicht mit einer
presentation,
Lupe anschauen, sondern es ist
the amazing immune systems. We're going to look in more intricately, even to a greater magnification. Peter Borger is going to speak to us about molecular systems. Today it's very relevant, and this Peter Borger already for many years, he's teaching in the different universities and very involved in research in this team. He's an expert in molecular biology and gene theory. And we're very glad to have you, and please come. Yes, we hear you. Mm-hmm. So, good evening to you. Welcome. Thank you that I can be here in Switzerland, in Kersatz. I was invited about a year ago to come today to speak to you. That time, the theme of immunity was very, very in vogue. It's a very, very interesting theme. And so today, this evening, immunity. I know quite a lot about immunology because I've studied and researched for many years about asthma and lung issues. In Holland, I've lived and worked and did my study there, particularly with asthma. It's seen as an immune illness because the immune system doesn't operate as it should. That's why I got to know about the immune system, and I got to know which cells are actually involved. So here I'm showing you a crowd of people, a great number of people, crowd. So, how do we know people in the middle of this crowd? We have certain senses for this. We have eyes, we see, and we acknowledge and recognize our friends. And we see here also people that we don't know. We can maybe even recognize here people who are our enemy. We see, and with our eyes, we recognize certain things. Now, cells, they have no eyes. How do they recognize? How does the immune system recognize what is belong to itself and what is not? Because if the immune system doesn't recognize its own and attacks them, then we have a problem. Like if we would attack our friends, we would have a problem. Yes, enemies we should attack, but when you don't have eyes, how is this recognized? How do we know, how does our immune system recognize what is belong to us and what is the enemy, the intruder? If you look carefully here, maybe you'll see something here. If you really look, you can maybe see there that I'm there in this crowd. You have to really look, but the immune system is capable to recognize in the crowd this intruder. This is an important question. How does the cell know? So tonight, I'm going to look at the layout. Firstly, an overview of immunity. What is our immunity? It's like a fluid organ that works together. What is it, our immunity? It's an important question. Where do immune cells come from? You know, after conception, one cell is formed. The immune cells come also out of this one cell, which is the beginning. The important question of the evening is, how do we recognize what belongs to us and what's a foreign to our body? Antigen and antibodies. We've heard maybe this word, antigen and antibody. We're going to look at the T cell receptor and the MHC system, the major histocompatibility complex. The thymus gland and what's called the complement system or the innate immunity. Maybe you've never heard of these things, but it's a very important part of our innate immunity. And every time when I have a little light bulb, there's something here that's a design feature of the immune system. If you leave away one cell, everything changes. It doesn't work. This is an incredible complex system in the immune system. So we're going to look at the genes that play a role in all of this. And there are billions of antibodies. It's so important, so interesting, this story. And these are the themes that we want to look at this evening. The immunity, the immune system. So we can say roughly it consists of two subsystems. The innate immunity and the acquired immunity. So the innate immunity is part of who we are. And yeah. But on the other side, we have acquired immunity or adaptive immunity. And that's very specific and it's acquired. In the course of time, our immune system adapts to an intruder. The innate immunity, or with which we're born, is already there. It's not specific. It attacks all general intruders. It doesn't acquire or adapt. It's already inside of our genes. And it's there and will be activated as needed. And in part of this innate immunity, with which we are born, there are different also subcategories in smaller compartments. We're going to go in and look. It's like in a classification of animals. We do this with people, and in our immune system also we have certain things that are subclassified. And the innate immunity is subcategorized into diverse classifications. Part of all of this system is our skin, which is there to keep all things that should not intrude into our bodies, keeps them out. And in this layer of skin, there are also many parts of this immune system. And anything that will come through will activate the immune system, and those cells come to deal with the situation. So I want to look at the immune organs. So in the skin, there's a system. We see here is the pH. It's kept in a certain place so that the good bacteria, the hout flora, the skin flora, can thrive, and that the unhealthy bacteria will be restricted and restrained. We want our skin to be populated with the good bacteria, which also then restrain the other bad bacteria. And all these things, for all of these things, certain elements must be produced and secreted so that it can be good controlled and regulated, this whole flora and system. Then there's also those phagocytes. We're born with these. They are cells that eat. Everything that does not belong to the body itself. But we want to know, how do these cells know the difference between what belongs to me and what is an intruder? We're going to look at that later. Then we have the RECs. They're in our vessels. I'm not going to say too much, but they have also a very innate function. We have also inflammation. It's like inflammation. The temperature, it would be raised, like fever. Fever is brought by our body so that we can, it's an antivirus mechanism. When a virus begins, we become sick, we have fever, and this virus the virus will be dealt with by the immune system. We won't feel good in this process. And then we have the natural killer cells, that's the NK cells. So you think they're natural destroyer cells, which will attack everything that is recognized as foreign. Natural kill cells. And then there's the interferons. These are messenger cells. They go and give a warning in the area. They warn the neighboring cells. And this is all part of the innate immunity with which we're born. And this complement system, we're going to look at that later. It's a very important system, existing out of many different proteins that work together. For example, the bacteria, they can cause these bacteria to explode. Very important. So all of this is part of the innate immunity with which we're born. And already here, I could say, here all 95% of every intruder, bacteria, parasite, virus, can be dealt with by this innate immune system. And then we have the adaptive immunity, the acquired immunity, to which belong the B cells, these antibodies. And when, for example, with the vaccines, these different antibodies are raised up through vaccines so that here it's a humoral immune response is the fluid in the body and in which our antibodies are found, the humoral immune response. On the other side, we have a cellular immune response. These are the T cells. T cells are very important. That's my doctorate work that I've done on this area. The T cells have different forms. They can immediately attack infected cells and destroy them. They can also regulate the whole immune system, like a conductor. You can think the immune system is like an orchestra that plays together. Everything has to be in order and in tune. And these T cells can direct these processes. So this is just a rough overview so that we have an understanding of the immune system. There are different parts, and this here is not just in categories, but works as a whole homogeneous system. The innate immunity is dependent to a certain degree from the acquired immune system. And we see that this is a whole system of cooperation between cells and molecules. They work together. When you look at this, it shows here, yes, I have a little light bulb there. All of these parts must work together as a unit for the whole thing to function properly. The whole system it's a whole system, a one system. You can't say this part is important or that. All of these cells have to work together. This cooperation, working together. So I have a light here, light bulb. It's to show that it's a design feature of this, an intelligent design, this immune system in itself. So that's the overview of our immune system. Now we look a little bit in a deeper way. Here I've present a castle. It's a castle close to us in Lörrach. It's like a castle or a festung. We have unspecific defense, rocks and water and walls and pits and so on. So that should help also against specific anything that would come to try and intrude. On the other side, we have very specific defenses. So very specific then, we have soldiers and weapons and arrows and burning oil. This is a specific defense. So we can see this. This is like our immune system, the unspecific and the specific. And so it's also in us, in our human body, we have specific and unspecific defenses, lines of defenses. We have the mucous membranes, the nose, everything that we breathe in the lungs, dust, and it's given again out and is destroyed by the cells. So that would be, for example, non-specific. On the other side, we have specific. And where the specific defenses we have? In our lymph nodes, in the T and B cells, in the lymphatic vessels, in the lymph nodes. You can feel them if you have an inflammation or in a throat infection. Or here on the different glands, we can feel that they are sensitive. That means there's a battle going on. And this has to do with an intruder. And the B cell and the T cell are coming and the antibodies are activated. And also in our tonsils. It's an important organ for the whole immunity. Earlier, my tonsils were removed because we thought they're just extras. We don't need them anymore. They will never be removed now. We understand it's part of the immune organ. When you look back 50 years, we didn't understand the immune system. We thought, no, it just works like that. In the 60s and 70s, we began to study the immune system. And now it's a whole area of science and biology. It used to be all just part of the study of blood, hematology. But these have a very important function, the tonsils too, and they won't be removed anymore. The thymus also, and the spleen, and the appendix, all important organs that we haven't understood. We thought they were just leftovers from an earlier age. The thymus, for example, is only there for the first 20 years of our life. And then after that, it just shrinks and disappears. And we thought, well, we thought, okay, we can get rid of it if we don't need it really. They're leftovers. But now we know the thymus is a very important organ for the training the immune system to know what is belonging to the body and what is foreign to the body. The spleen will also sometimes be removed. This is like a storage place for the immune system. And the function is taken over then at some point by other organs. But the appendix, for example, we thought also this is another leftover, unnecessary organ. But today we know we need this. We need the appendix. It's a part of the response of the immune system to different phases. Second, it's a storage place for important bacteria. Without this bacteria, we can manage. But when we really understand what's going on, all of these bacteria will be taken out of this appendix and brought into action. So now today also this appendix will not be removed. Now we know it has an important biological function. All of these organs, in a short time, suddenly we realize they have an important function in the body. So today, we understand. Also, the bone marrow, it's very important. All the blood cells are produced in the bone marrow, including all the immunologic cells. That's why we could call the bone marrow an immune organ. So again, what is our immune system? It's our body's natural defense against foreign material. Could be anything, microbes and viruses, everything that we can breathe in. Without an immune system, microbes would quickly take over our bodies and destroy them. Escape very quickly. When someone dies, after one day, they begin to stink so quickly. This is because the bacteria have overcome the body. So our immune system is incredibly important. We have 3 different immune levels of immunity in our immune system. We have this innate immune system. For example, when we have inflammation and fever. So 3 stages of defense against foreign invaders. Part of our immune system is the skin, and it's a waterproof physical barrier that hinders the penetration of particles and pathogens. Also, the mucous membranes keep the body safe in the nose and lungs. They trap particles and pathogens, and then they remove them by kinetic processes, by hair movements and coughing and so on. Also, pathogens only can penetrate if the skin is damaged or if the mucous membranes are damaged. So the skin and mucous membranes are very important as part of this immune system, not to have any wounds. Then the innate immune system with which we're born, inflammation and fever is part of this reaction. So non-specific reactions to different particles and microbes and tissue damages, this is the complement activation. I'm going to later explain how that works. In the inflammation then, this is how immune cells are recruited. The granulocytes, the macrophages, and the isolation of the various pathogens. They're encapsulated, they're recognized, and they're destroyed. That's all working together with the complement system. Because the complement system marks these foreign bodies that have intruded. And fever then, it prevents the growth of microbes and accelerates the tissue repair and kills the virus. This raising of temperature is normal, not too high. It shouldn't go over 40, but about the 40 degrees Celsius, then the viruses are destroyed, killed, and the tissue is repaired. And so these foreign invaders in our body are destroyed by the immunity. And then we have acquired immunity. It's a very specific defense which we acquire over time, and it involves 3 steps. First, there's the recognition and marking. They recognize, is this an intruder? And then it will be marked. Mostly with antibodies, they're marked that connect to them. And then the cells come that eliminate them. All of this working together, they work all together. And when it's then eliminated, there's still another cell that is a memory cell to remember that this cell has come before and we know who he is. There's a lot of memory involved in that, the memory cells. There are B and T cells, which are also memory cells. The whole immunity and when all of these bacteria have been eliminated, there's still a handful of these memory cells active, so that if this bacteria returns, there's an adequate response. Also, we have here in the acquired immunity B cells, where the antibodies and the immunoglobulins are produced. The T cell also work in a very similar way to produce the antibodies. I'm going to explain later why we have T cells. And they're called T cell receptors. They're like little hands. They grab something and they never let it go. That's the T cell receptors. So we're going to look now, where do these immune cells come from? I said already, they come from the bone marrow. Like all other blood cells come from the bone marrow. So here we see, you see there? So today we have a little issue. We're not finding the things we should see here. So here, all these things are cells. They all come, they're coming from the bone marrow, from the stem cells. And they divide into 2 classifications. The lymphoid stem cells and the myeloid stem cells. The myeloid stem cells, they develop also all within the bone marrow. They develop into myeloblast and then continue within the bone marrow to develop into many different types of messenger cells. And which cells do we have? In the right environment, within the bone marrow, we have blood cells, we have the platelets, we have also the granulocytes, very important cells for the first dealing with defense. When an intruder comes, the neutrophil are the very first cells to react. And they're on the very front line, coming from the white blood cells, 70%. And if you have a blood sample and you see a lot of blood cells, they are neutrophil cells. They also, these myeloid stem cells produce the macrophages, very important cells in fighting against bacteria. The macrophages are also eating cells. They eat a lot. Macro is much, and phage is to eat, to fight against the foreign intruder. On the other side, then, we have the lymphoid stem cell with the right conditions and the right messenger. The lymphoblast is formed, which develop then further into T cells and B cells, the natural killer cells, the other side. So this is a rough overview of the stem cells in our immune system. So about 8 cells here. And how are they involved? So there's a specific immunity or a non-specific immunity, with which we're born. And all of these natural killer cells and the eater cells, they destroy the invading bodies. So we have these are the immune cells. We have that all belong to the innate immune system. And the other side then is the acquired immune system. We have the T cells, the B cells, and then natural killer cells. And the B cells too, which produce the antibodies. We're talking a lot about the B cells and their antibodies in the first line of defense. It's already a very immediate response is produced, and all comes from the immune system with which we're born, and then the adaptive immune system is reacted then when it has a specific problem to deal with and produces the necessary antibodies, the B cells. Everything works here together. And I said before, the T cells have a very important function as directing this system, this operation. They have to work together for the whole to function. Here I have my little light bulb, because I say that one cannot happen without the other. There must be a working together, a cooperation. The cells in the body have to work together, all, so that our body can function. We don't feel it, but it works the whole day long. The cells, they recognize each other, they work together, they function together, and they produce an immune response. So now we're looking, how does my cell know the difference between what's belonged to itself and what's foreign? We see a castle is defended by an army. And in the old times, we knew one another. How did we know? For example, with a shield. They had a shield, the same shield maybe all. And then they said, oh, look, this one has this shield, these are my friends, and this other shield, this is my enemy. In all the different lands, all the different dukes, lords, all the counties here in Switzerland, all had their own armor and own flags. So I took here, and I said, I show you here, we can understand. All of these are our immune system. I put on the cell, we have the Swiss cross. And we know, okay, this is ours. That's a friend. You can imagine every cell has its shield. And then we have these T cells that come by. And they also have a part that responds, a shield that's also a Swiss cross. And that means it's recognized as a friend. And then they don't do any problem. They have no problem with each other. They're happy. They don't attack these cells. They've been recognized. They belong to this body. And then when a virus comes, we see, okay, the virus comes and it infects one cell. What does the cell do now? And it comes onto the shield, something that shouldn't be there. And it's there on the shield. And then come the soldiers by, the T cell, and they recognize that is this ours? This belong to us? No, something's different now. So the two are happy. These cells are accepted. They're not going to be attacked. But this one in the middle is not recognized anymore as from the own body, because the shield has changed. So you can imagine. And now what's going to happen? He's not happy. This cell will be attacked, will be killed. We see the same thing in our bodies. This is a good picture for us to keep in our mind. It's a lot more complex, of course, because there's a lot of proteins involved. These shields are actually proteins. These are called MHC molecules, very complex proteins. And they are shown on the membranes of the cell like a shield. That's what I was trying to show you, illustrate. We have MHC1 and MHC2, two different cells. The MHC class 1 is like a shield 1 on every cell of your body. Will be recognized because of MHC1. And the MHC class 2 is also a shield, but it looks a bit different. And that comes on the antibody-presenting cells. And this can come to cells which could possibly be foreigners. So what is antigen? What is an antigen? It's nothing else as an antibody generator. It's like it creates antibodies. Everything that's a foreign intruder is seen as an antigen, antibody generator, because it causes antibodies to be produced. So here we have an antigen. If there's nothing there, nothing presented, no protein presented, the T cell is coming, sees nothing's going on, and he just continues. No problem. Now we have no immune response because the shield is clean. There's nothing on it. But then what happens when a virus is there? As we've seen, the virus which is here depicted, it's come into the cell. It'll be disassembled by the cell and will be captured and taken on to the membrane. And now it's on the membrane and the shield has changed because a part of this virus is forced to be taken onto the cell. And when now the T cell arrives, it's recognized as because of toxins. When he comes by, he sees it's not recognized as his own because the shield has changed. The protein shield is different. And now what happens? what I've shown you before. This cell will be attacked and will be destroyed in apoptosis, which is a programmed death of the cell. And it's like a suicide of the cell, disassembling the cell. That's how it functions. Also on a molecular level. This is how these bindings happen on the membrane. The cell produces this. It's a small part of the virus is displayed on the shield. That's how we can imagine this process. These T cells are continuously patrolling, checking out all the different cells if something has been captured. So now we have an antigen specialized cell. What is it doing in the blood cell? When it sees something foreign, it'll be captured and then presented with a different shield. It's very similar, but still different. I have a shield. Here I have a little bit of virus on it. When the T cell comes by, this is it's a helper T cell. And here we have, what does the helper T cell do? They first inform through the use of other molecules, like the CD3, together with the CD4 and CD28, the T cell receptor. But there are other molecules also that work together. What do? They present a connection and they transfer it to the cell, and if there's a good, seen as good, then the T cell receptor and the CD28, very important connections that happen, and then a signal is produced in the T cell so that the different activation happens in the genes, and the messenger cells, they produce what's called cytokines, and through these messengers which are produced, the granulocytes are involved and help to make the other cells active and to make the immune system, the monocytes, all are brought into action. And the helper T cell directs the whole process. So the T cell is directing the whole immune response. Also, the cytokines can cause the plasma cells to be activated. They're mature B cells. They're like factories and produce antibodies. There's thousands in every second that are produced. It's like a big factory that's producing millions of these antibodies. So these antibodies are very specific to this foreign invader, and they are continuously produced and multiplied until there are millions of antibodies engaged. But the B cells can't happen alone. They need the T cells to bring all of this process into being. The AIDS virus, the helper T cells would be destroyed, and there's no possibility to direct the immune system all of these cells are around about, but there's no music. So the helper T cell has a very important function in our immune system. Here again, I have a little light bulb, because all these cells have to work together. It's to produce an important immune response. They have to work together and to do the right thing. Everything is minutely tuned. All the different important cells have to be there, and the immune response comes into its fullness. So we have the different cells, the helper T cells, the cytotoxic cells that connect with the MHC1 cell, and each cell is inspected with what's on their shield. The processes are quite similar, but just with different molecules which are displayed on the shields for different situations. So, what belongs to the body and what is a foreign? The MHC molecules are the shields. I have a shield. This is the process again. You recognize my shield. If it has something on it that doesn't belong, it'll be recognized, and this cell will be destroyed, and the antibodies will be produced, and this is the immune system at work. I brought here also, we look at what's the T cell receptor. It's the party that complements the shield on the other side. We have the antibodies. They look very similar, the T cell receptor and antibody. The TC receptor only is on T cells. It's about knowing what belongs to the body and what's a foreign intruder. And the antibodies, I haven't explained a lot about it, but it's got to do, again, with recognizing what's foreign, what's native. But I won't go into it because it would make this presentation too long. All of these antibodies are all over our system, in our blood, and they patrol, and they can connect different cells, and then these cells will be stimulated, and also when viruses connect with these cells, other cells are activated. The B cells, the natural kill cells, the granulocytes, all of these different cells that are part of our innate immune system with which we're born, all are brought into action. This is a cooperative system, all this system working together. It's a whole system and works in unison, and only works optimally when all work together, all components. So I want to look at these T cell receptors. We can ask ourselves, there's an incredible amount of foreign bodies which are foreign to our body, molecules, millions of molecules. They're estimated to be millions. So millions of molecules, all foreign to the body, which we breathe in, and they could damage us. And where do all of these incredible amount of antibodies come from? They are proteins. How can they be generated? So many millions of these genes. And how can so many different specific TCRs and antibodies be generated? Are there millions of genes? No, we don't have millions. If we have about 20,000, maximum 20,000 genes. If we don't have millions of genes, so there must be something in us, in our genes, that work produce this. It's called gene rearrangement. Also, we find the same for B cells. It functions in the same way. I'll show you, I'll put it here again a little. So I'm going to explain it to you. We have T cell receptors built from different genes. Here we have them, V, J, and C. If we have 50 V genes from the V area and 100 genes from the J zone and one of the C, then we have 50 times 100 times 1 when we bring together. We can have 5,000 different types of TCR cells. And in the B beta chain, if the 60 times 6 times 1 times 6 times 1 gene and comes to 2,100 genes. So from one T cell receptor, we could produce hundreds of millions, 10 million different TCR cells. It's more to do with the mechanism of how they're combined to produce millions of genes. One mechanism creates millions of different TCRs and antibodies. That's Datenkomprimieren. Don't have to code everything. We can have a system that compiles all of this. It's a very also a clear sign of intelligent design. So where do all these T cells come from? We've spoken about the thymus. Is it from there? It's a training system. It's a system called gene rearrangement, recombination of DNA, which produces so many antibodies and T receptors. In this organ, there's a positive selection where lymphocytes that can recognize the body's own molecules, these MHC, the shields, and then they are multiplied. All others that are not recognized are destroyed. They disappear. Only the T cells that have this shield that is recognized are allowed to be part of the system. So it's positive selection. But there's another selection step in the selection. It's negative selection. These are lymphocytes directed against the body's own antigens, the proteins, and they are sorted out and destroyed. They're not allowed also to be involved. So we have a population of T cells, millions of T cells, that only recognize their own body as itself. But if they attack their own body, we have an autoimmune illness. So out of a handful of genes, with this mechanism, millions of genes and millions of cells are produced. And how does all this work? We spoke already about the thymus. These 3 steps occur. The gene rearrangement, how genes are recombined. This all happens in the rinde or the cortex, and in the medulla here, as you can see on the graphic. The negative selection also happens here in the medulla, and the cells that are not allowed to be participating in this process, that's called apoptosis. It's like a suicide of the cell. They have to be destroyed. There are also apoptosis bodies. a process happens where these cells kill themselves. In the bone marrow, all of these precursor T cells are produced and are transported to the thymus, and there then this training happens. So as we see, the thymus is not just some kind of an extra part, unnecessary part. It's a organ, very important, where all of these processes take place for the training and for the multiplication. So we see the precursor T cells are the ones which are able to discern very faithfully, capably, what is belong to the body and what is foreign to the body. And so because of the thymus, the body's own system is not attacked. It's what's known as self-tolerance, where the body's own tissue is not attacked. And the matured T lymphocytes spread from the thymus in the blood. And so I'm going to just look again, come again to the overview. The whole immunity works together, the innate immunity. Now we want to look at the complement system. Almost all intruders are attacked. Complement system is here again very simply presented. What is it? Here's it's a simplified version of how the complement system works. It's very complex proteins. We have 6 proteins here. It's an activation, a cascade of activation happening here. These are different sugar groups, the manana, the antigen. And when the C1 is activated, everything just starts to work on its own. And the C1 activates C4, which activates C3, and process goes on, C5, and all of that. This bacteria will be occupied with a certain membrane, which makes a hole in the bacteria. And when there's a hole in the bacteria, water will be drawn in automatically, and the thing just bursts, this membrane attack. And then the different feeding cells come and they eat up this cell. And then, so that's how it works. And then they'll be eaten. The whole system has recognized what's foreign. So microbes are able to be dealt with in this system 95% of the time. Here again, the whole complement system looks at the different viruses, microbes, everything works together. If anything is missing here from the C molecules, we already have a problem. Certain reactions won't happen. And then we have infections. Everything has to be dealt with, work together. I can also here again put a little light bulb to show here again incredible design. So we're coming to the end. As we've seen, we have certain organs, the thymus, very specific organ, also in different mammals. By different type of these organs. sudden appearance. These organs have suddenly appeared of the immune system. There are very clear boundaries in the immune system. And suddenly something else comes. New and complex organs, part of this process. Here we have this Darwinian evolutionary process cannot produce these incredibly complex organs and systems we see in certain type of fish. So we see very clear boundaries and new and complex organs. Again, it points to intelligent design. Can't happen on their own. No, it's not. Doesn't work. These are integrated, complex systems that work together. Engineering, incredible engineering feats. So, sudden appearance of these organs of the immune system. No. We have seen also genes of tiny sea creatures. When we're looking at the evolution of immune system, can it happen? If we look at different publications, the immune proteins, 3D structure similar to V genes, but they don't have typical genetic features of antibodies and T cells and the receptors. All of this just points to creation, not evolution. But what's written in the popular scientific publications, you have to be careful of what's there. So here again I have this little light bulb to show. Again, Roger had also spoke about it, redundance. Redundancy, it's a certain robustness in the systems. Every intruder will be 4, 5, 6 times will be attacked from different systems. Viruses, no. Also, maybe 6 times from different cells working together. Cooperation. The redundancy is important. It shows it's a display of intelligent design. So we see also cooperation, the molecules working together, not egoistic cells and genes, all working together, the cells. So many billions of cells, and they all working together. We don't have any rebelling cells have to be destroyed and removed. Cooperation, so important that the cells work together. Also this non-reducible complexity. The individual components that often they can't be removed from the system. Otherwise, the system as a whole will not work. We have problems with infections and problems. Also, we see data compression with a few hundred genes produced. Millions of genes are produced. How does that work? There's a compilation that's happening, like through information and proteins, with a PowerPoint. If you look at the cells, how they are produced and developed, it's just incredible. Unbelievable design. And then, of course, when we see a sudden appearance of immune organs, like the spleen or the thymus. Suddenly there's a whole new organ there, like the TCR. New organs is inexplicable. We can only attempt to explain an organ is an organ. So we have so many pointers that point to creation. And so I want to close now. I'm so thankful that I can tell people how wonderful, how incredible the creation is. Our amazing immune system. We should be thankful we should thank our amazing God for this amazing immune system. And without that, we wouldn't sit here for long. So I'm thankful for your attention. I think I've gone over the time a little bit. I hope what I've spoken has you've been able to. Our God is a strong refuge. Here we have again science, which is on God's trail. These are different books you can read, what our God has created, what are the different the testimony of God. We live in a time when all of these things are being revealed. And so I close now, and I want to say thank you for this evening.
Vielen herzlichen Dank, Peter. Du hast überzogen.
So, thank you, Peter. Yes, you went over the time, but yeah.
Wir machen eine ganz kurze Pause, dann geht es.
We're going to make a short break, and then we continue.